Hello students, my name is Sumit Sagar Hota. I am a PMR PhD student at IIT Palakkad. Today we are going to discuss lecture 26 to 30 by Professor Ashok Desai of IIT Kanpur of the subject Introduction to Airbreathing and Propulsion. This is the week 6 of the live discussion section. In this section we will solve some of the MCQs and at last we will solve one problem. Okay, so just let's start the section. The axial flow of turbojet have about dash less specific heat fuel consumption. Okay. So this is a kind of theoretical question. You need to remember all these values. Like this for this question, the answer is A. Okay, which is 6 to 8%. Okay, so yeah, just quickly go to the next one. The basic cycle of turbojet engine is what? Okay, so all these kinds of turbojet, all these engines are having. We know very well it's Brayton cycle or otherwise known as Joule cycle. Okay, any kind of turbojet engines. And it should be noted that both are same. Okay, okay. Next is turbojet engine is a dash. It's a continuous flow engine. Okay, there will be continuous fuel and air supply, and there will be continuous combustion happening. Okay, in this engine. Okay, continuous flow engine. The turbojet engine is eminently suited for propelling aircraft at speed what? Okay, it's nearly 800 km per hour. Okay, uh, any kind of turbojet engine. Okay. In commercial aircraft, you can see the optimal speed we are actually operating is some 700 km per hour. Okay, it's the same speed. Okay, more or less the same speed. should be noted that it is the maximum velocity they are talking about. Okay. But for fuel economy, it's generally we are operating less than 800 km per hour. Okay. If it is asked for a fuel economy condition, then it will be below 800 km per hour. Okay. The turbofan engine was originally conceived as a method of improving the dash of the jet engine by reducing the mean jet velocity. Okay. Okay. So, talking about the turbofan engine. Okay. Okay, so what are the methods of improvement in the turbofan engine? Okay. By reducing the mean jet velocity. Okay. That means they are talking about they need to reduce the if your jet velocity will decrease, then they are talking that if the jet velocity will decrease, then what is going to happen in all these different parameters. Okay. So so if the jet velocity will decrease, so in general we just know the jet velocity will decrease, there is a chances of increase in what, the propulsion efficiency. Okay. For what? Turbofan. Okay. So efficiency, propulsion efficiency of turbofan is inversely proportional to the jet velocity. Okay. So this you should remember. Okay. So your this propulsion efficiency will increase. Okay. Very important. This they can ask like it will increase, decrease, that way also they can ask. Okay. Next one. The turbofan engine are usually described in terms of dash. Okay, so it's a very good question. They just try to confuse you by putting the term bypass. Okay, bypass ratio, factor, all these things. Okay, so just let's discuss about what is this bypass, factor, ratio, all these things. Okay, this bypass having two terms. One is the ratio and one is the factor. Okay, so first let's talk about the bypass factor. Okay. Let's the ambient temperature, the inlet temperature is Ti, and there is one kind of open environment or kind of heater, you can tell. Okay, one heater is there which is having a temperature of Ts. Okay, the inlet temperature is Ti. When after the when the gas or when the air passes through this heater, the outlet temperature is let it be To. Okay, so if we can plot these things in a graph. Okay, so Ts we are assuming is at a fixed temperature. Okay, from starting to the end, the Ts is fixed. Okay, okay, this is time versus temperature. Okay, now when the time passes, this Ti, okay, and Ti is equal to T ambient, your atmospheric temperature. Okay, ambient temperature. Okay, is actually at here. Okay, so maybe let it be here. Okay, so this is your Ti is equal to T ambient is equal to, let it be 298 Kelvin. Okay, this is in Kelvin, absolute units. This is in second. Okay, so when the time passes, this Ti is going to increase because it's passed through this heater. Okay, and which is having higher temperature of Ts, where this Ts is greater than Ti. Okay, for that condition, this the Ti will start to rise. Okay, and until outlet it's going to rise. Okay, then it is become what, constant. Okay, but it cannot touch to the Ts because it's required infinite time to be stay there to reduce the temperature of what, Ts. Okay, so in infinite only it can touch. Okay, the graph can be look like this. Okay, okay, in infinite only they both can touch. Okay, so yeah, you can put directions also. So this is up to infinite. Okay, okay, in the similar manner, so this is for your Ts greater than Ti. Okay, okay, now instead of that, if your instead of that, if this Ts is lower, okay, or this is not a heater, it's now become a cooler. Okay, or AC you can think of. Okay, outside temperature Ti is high and Ts is actually low. Okay, Ts is now less than Ti. Okay, AC is going to cool the room. Okay, similar kind of condition we think of. Okay, okay, that means this Ts is now actually fixed. Maybe the AC is now maintained at a temperature of some 20 degrees Celsius or something like that. Let it be 20 degrees Celsius, or it will be 20 plus 273, or let it be 10 degrees Celsius. Okay, so 10 degrees Celsius means 284 to 283 Kelvin. Okay, so okay, so Ts is maintained at 283 Kelvin. Okay, and it is actually going to maintain at the end of the time. That's we are assuming. Now Ti is actually a hot gas. Okay, so Now when this affected through this Ti, the temperature is going to reduce, but it cannot reach to the this 283 Kelvin, and it can only reach at the infinite. Okay. 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 So these are two kinds of conditions are there. Okay. So so now for this kinds of, when these kinds of change in temperatures are there. Okay. And that when this atmospheric temperature, the inlet temperature, the outlet temperature, and the surface temperature of the heating coil or cooling coil, all these things are when talked about. Okay. Then one term we just tell, that term is called your bypass factor. Okay. What is a bypass factor? Okay. The bypass factor is the temperature drop or increase not achieved divided by temperature drop or increase that could be ideally. Okay. So what temperature we didn't achieve? We didn't achieve the T outlet temperature, right? It cannot achieve through the TS, right? So this TS minus TO divided by, but we can achieve TI, right? TI is going to be change. Okay. TS minus TI. Okay. So TI is going to change to, try to change to TS, but it cannot change, but it can only reach to TO. Okay. So this is how the bypass factor is defined. Okay. And this bypass ratio is also a similar way it can be defined. Okay. The bypass ratio is equal to flow through the bypass duct, which is a cold stream, divided by flow at entry to the high pressure compressor, which is a hot stream. Okay. Okay. So this is how your bypass ratio is defined. So basically, if you can see, this is a kind of flow. Bypass ratio, it deals with the flow phenomenon, and bypass factor is a kind of change in temperature phenomenon. Okay. So this can be written as m dot c, the cold stream flow to the hot stream. Okay. So in okay, so when we can define also total flow, m dot total is m dot c plus m dot h. Okay, so now how questions can be asked? They will give you ts, they give you to, and they give you ti, and then they're just going to ask you what is the bypass factor. Okay, or basically this bypass factor is a more specific to the refrigeration. Okay, if you have taken any course regarding the refrigeration system, this is how related. Bypass ratio is related to our course. Okay, I shown you both because so that the idea and the confusion will be clear. Okay, in our course this bypass ratio having a huge importance. Okay, and how the questions will be asked, like they will given you the total mass flow, and then ask you what is the mass, what is the cold stream mass flow, or what is the hot stream mass flow. Okay, or they will give you both m dot total and br, and they will ask you what is m dot c or what is m dot h, like that they can ask. Okay, so the one more formula I can give to find out the m dot c is equal to m dot total into br divided by br plus 1. Okay, and m dot h is equal to m dot total divided by br plus 1. Okay, this kind of questions can be very easily asked. Okay. Okay, let's go to the next one. Now this question is very simple. Okay, bypass ratio defined as the ratio of the flow through the bypass duct to the flow at the entry to the dash. Okay, obviously high pressure compressor I already told. Okay. So it's very difficult, means very easy to remember. For you see, then the how they just try to confuse you. They given also high pressure compressor, here also high pressure compressor, but one they to given hot, one they given cold. Okay, always remember high pressure compressor. Okay, that the pressure is already always going to be high. Okay, there is no way the temperature can be low. Okay, so that's the reason this option is very well, it will be wrong. Okay, low pressure anyway going to be wrong. Okay, so this is only the our option answer. Okay. Okay, so the term turbofan was originally used for engines of high dash. Okay, the turbofan was originally used for the engine of high bypass ratio. Okay, that means it can handle, it can take more cold stream, okay, of air and produce more with and produce more work output, and in such a way there will be more combustion efficiency and propulsion efficiency. Okay, so that's the objective. Okay, just read this question. Determination of the specific thrust. Okay. Determination of the specific thrust and specific fuel consumption for a simple turbojet engine having the following components performance at the design point at which the cruise speed and altitude are Mach 0.8 and 10,000 meter. The compressor pressure ratio, turbine inlet temperature, isentropic efficiency of the compressor, turbine intake, propelling nozzle are given. The mechanical transmission efficiency also given. The combustion efficiency given. The combustion pressure loss is 4% also given. Okay. We need to find out the specific thrust and specific fuel consumption. Okay. Okay. So let's write down what are the things given and hmm. Let's just start solving. Okay. So in the question, if you see, it is written. Okay, in the question, it's if you see that asking about the thing is in the question, some of the things are not given. Okay, so that's the thing. So in exam, they should give all these values. Okay, like at they're specifying at 10,000 meter. Okay, but 10,000 meter, the properties of pressure, temperature, and the velocities are not given. Okay, yeah. So the things they should give is at 10,000 meter. Your PA 0.265 bar. PA should be 223.3 Kelvin, and the speed will be speed of the sound 299.5 meter per second. Okay, either they should give you one table where these all three parameters are there, or they have to directly give you the values at 10,000 meter. Okay, then only you can solve this question. So let's start the solution. So the Okay, so whatever the engine it might be, okay, we are assuming it as design point at which turbojet. Okay, for any kind of turbojet engine, we always assume the what we are it's operating in Brayton cycle. Okay, so let's first draw the Brayton cycle. Okay. Okay. Okay, let's draw the TH diagram. Okay. Okay, so this is your A ambient state. Okay, then there will be one state. Okay, then there will be one two state. Okay, then there will be one three state. Okay, then there will be one four state. Then there will be one five state. Okay, it's not a simple Brayton cycle. Okay, so but the processes are same. Okay, like A is here, this is your one, this is your two. Okay, and then they are talking about one combustion pressure loss. Okay, of 4%. Okay, here that pressure loss will come between 2 to 3. 2 to 3 there will be combustion. Okay, okay. Then from here to here, this is 3, this is 4, but now 3 to 4 there will be some losses like isentropic storms are given. Okay, isentropic efficiency of the turbine. Okay, and then intake and propelling nozzle. Okay, all having different losses are there. Okay, all losses we should consider. So it's not now 3 to 4, it will be 3 to 4 dash. Okay. Okay. This is your 5. Okay. Okay. So just let's start solving. Okay, so let's find out one term called stagnation condition after the intake. Okay, okay, so for that we're assuming the ambient condition, that is Ca square by 2 times Cp. Okay, Ca is here Mach number into the speed of what is given at 10,000. Okay, m into a, okay, m into a square by 2 Cp. Okay, so which is equal to 0.8 into 299.5 square. These are 10,000 meter, we have a value, right? Okay, and 0.8 we already from here. Okay, Mach is 0.8. Okay, I just substituted here. Cp value is 1.005. Okay, it's not given. Okay, if it's not given, Cp always remember kilojoule per kg Kelvin. Okay, okay. So Cp is 1.005. We need to convert into SI units, so just multiply 1000 so that it will be joule per kg Kelvin. If you solve it, you will get it is 28.6 Kelvin. Okay. Okay, so now why I find it, because we need to find out the T1. Okay, and T1, for T1, finding T1, this stagnation condition after the intake is required. Okay, okay. So T1 is equal to Ta plus m dot C or m dot A square divided by 2Cp. Okay, now Ta, what is Ta? Ta already given 223.3 Kelvin. Okay, so okay, so it will be 223.3 plus 28.6. Okay, so T1 will be your 251.9 Kelvin. Okay, so okay, now let's find out now P1 and P2. Okay, then from that P1 and P2 you'll find out the T2. Okay, that means we need all the parameters of temperature, pressure, everything. Okay, okay. One thing also you should assume that it, whatever this P5 will be there, okay, this P5 is equal to your ambient temperature, okay, because nothing is given, I am assuming it as PA or PC, okay, whatever you can tell. Okay, PC means your critical pressure. Okay. Why I am assuming, why I am taking all this, I will, when solving, I will tell. Okay, why I am taking this is as critical pressure or the ambient pressure. So, so now for this, we cannot actually apply your because it's not a subsonic flow. Okay, it's kind of it's actually subsonic flow, but here especially in these kinds of conditions where Mach number and all these parameters are given, especially turbojet engines, okay, we cannot directly apply the simple pressure ratio, or we cannot assume it as a isentropic flow. Okay, okay, okay. So yeah, instead of that, I can, because why I cannot assume it like this, because it's having some, this intake also having some losses. Okay, you can see the isentropic efficiency of intake also given. Okay, because of that reason it's given. But if it will be a simple Brayton cycle or simple Joule cycle, okay, of a kind of your diesel cycle, okay, diesel engine, then it will be, we just there simply apply P2 by P1 equal to T2 by T1 to the gamma minus 1 by gamma. Okay, all these formulas are very simple, so I'll just simply apply. Okay, but here these losses are, since these losses are actually we have to taken into consideration, the normal isentropic relation of pressure, temperature and volume is going to now change. Okay, okay, so like here you can see T1 and TA, how I write it. Similarly, the your P1 by PA will be the is equal to 1 plus isentropic efficiency at intake to Ca square divided by 2Cp into Ta, okay, to the power gamma by gamma minus 1. Okay, this is the formula. Okay. This will be applicable for any kind of turbojet engine. Okay, so in the question we have the intake efficiency 0.93. Okay, so intake efficiency we have, what we need again, Ca we need. Okay, okay, so okay, so we already know this Ca square divided by 2Cp. Okay, this term we already have, we know it. Okay, so we already know this term. Okay, what is the value of this term? 28.6 Kelvin. Okay, this is your 28.6 Kelvin. Okay, so and Ta you know very well. Ta we have here. Where is Ta? Ta is here 223.3 Kelvin. Okay, and what else? Efficiency, everything now we have, right? And gamma is 1.4 you take. Okay. Gamma is your 1.4 by 1.4 minus 1, which is 0.4. Okay. Now, if you solve this, you will get the value as 1.482. Okay. Now, PA also you know. PA 0.265 bar. Okay. So just find out P1. 0.393 bar. This is your P1. Okay. Okay. So now just let's find out the P2. Okay. Now, if you can notice in the graph, okay, picture or the TS diagram, you can see this 1 to 2 is a 1 to 2 process. We know it's a compression. Okay, in the compressor. Okay, so for 1 to 2 process, it's already one very one thing already given, so that it will be easier, like your compressor ratio, compressor pressure ratio given. Okay, which is 8. Okay, so compressor now operating in between which pressure, 1 to 2. Okay, so that means this P2 by P1 it's already given. Okay, which is 8. Okay, so P2 by P1 is 8 already given, and we have already what, P1. So you can just directly calculate P2 by multiplying 8 into 0.393. Okay, that Rp is equal to 8 is equal to P2 by P1. This is your compressor pressure ratio. Okay, is equal to P2 by 0.393. Okay, so P2 is 8 into 0.393. Okay, so P2 becomes 3.144 bar. So we have now P2. Okay, so next we have to find out what, T2. All the pressure, temperature, everything we need to find out. Okay, T1, T2, T3, T4, everything. Okay, then only we can calculate this, the specific fuel consumption and thrust power. Okay, so now P2 we have. Now let's find out T2. So T2 also not that much straightforward. We cannot directly take T2 by T1 ratio. Okay, T2 and T and temperature and pressure we cannot directly apply. Okay, so instead of that, we have one more relation. Okay, that is T2 minus T1 is equal to T1 by because in 1 to 2 process, which efficiency will come? Your compressor is operating, right? So for compressor, we have to operate it compressor efficiency, okay, which is 0.87. Okay, so that's the reason we can apply the simple direct formula. Okay, the difference T2 by T1, one formula already we know, T1 by just 1 second. Yes, so the formula is T1 by eta C into P2 by P1 to the power gamma minus 1 by gamma minus 1. Okay, so this is the formula. Okay, so now what are the things we know? We know T1. Okay, here we know T1. Okay, T2 by P1 you already know. Okay, okay, and eta C you know from here 0.87. Okay, everything you know, just substitute. 251.9, 0.87, 8 to the power 0.4 by 1.4 minus 1, which if you solve you will get 234.9 Kelvin. Okay, so this is your T2 minus T1. So now T1 also you know, okay, which is so now I can find out T2 is equal to 234.9 plus 251.9 is 486.8. Okay. This is your T2. Okay. Okay. Okay, so now what now we need to find out the what. Okay, now one more efficiency is given, is your what? Mechanical transmission efficiency. Okay, so this efficiency, what is the role of this efficiency, we need to understand. Okay, so when this transmission will taken into consideration, when there will be this, you know very well that the turbine is given giving the input power to the what, to the compressor. Okay, and by the this turbine power only this compressor will work. Okay, and this turbine and this compressor are connected in a closed engine. These both are connected through a shaft. Okay, we most specifically we called it as a transmission shaft. Okay, and that shaft, how much the input power given by the turbine, how much it can transfer to the compressor, are defined by the mechanical transmission efficiency. Okay, so this mechanical transmission efficiency is given. That means you just know very well the ratio of what? The compressor power to the power to the turbine power, or the compressor work to the turbine work. Okay. Always remember, in calculating the efficiency, always it will be output by input. Okay. Input we are giving through the, from the turbine we are giving input to the what? Compressor. Okay. Okay. So sorry, this is your turbine. Sorry, yes. Okay. Your turbine is operating between 3 to 4. Your turbine is operating. 1 to 2 your what? Compressor is working, operating, and both are connected through the shaft. Okay. So this is your CPA. CPG also not given. CPG will be your 1.148 kilojoule per kg Kelvin. Okay. Because the turbine is not operating in a normal gas. Okay. Because this gas having some higher temperature. Okay. And that having, and you know very well, the Cp is directly proportional to the temperature in the practical scenarios like this kinds of engine what we are now solving. Okay. In general, Cp is always a fixed value, but for a actual cycle, the Cp is a function of temperature, and more specifically, if I will tell, it will be in the order of a polynomial equation like a plus bt plus ct square plus dtq dot 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 up to nth power. Okay. T to the power n. So just put these values 1.005. We know always T2 minus T1 already we found from here. Okay. Which is 234.9 Kelvin. 234.9. Cp of the gas is 1.148 into 0.99. Okay. Sorry. What I done actually, I just put T3 minus T4. Okay. Okay. Let's just take the denominator to here. Okay. And because why I do done this, because we need to find out T4. Okay. Any other temperatures given? Yes, one very good temperature at least given. This turbine inlet temperature. Okay, you know very well 3 to 4 is your what? Turbine. So inlet to the turbine is the 0.3. Okay, that means in the question the turbine inlet temperature, okay, is given T3. Okay, so T3 we have now at least. So yeah, so T3 is your 1200 Kelvin. Okay, so yes. So if you solve this, you will get it as 207.7 Kelvin, and if you find out the T4, it will be 992.3 Okay, so now we have T3, T4, okay, and P1, P2 we have, so that we don't have P3 and P4. Okay, so that means we need to find out now P3 and P4, and also T4 dash. T4 we only have, right? In our cycle T4 dash is also there, right? T4 dash. So P3, P4 and T4 dash we need to find out. Okay, then only you can find out the our final expression. Okay, so okay. So now how to find P3? Okay, so now if you see in this expression, we have actually one pressure loss between 2 to 3, okay, which is having a value 4% compressor delivery pressure, combustion pressure of loss of what, of 4%, okay, due to the compressor and this is due to the compressor delivery pressure loss, okay, okay, which act as a combustion pressure loss. Okay, so yes, so from here we just get the hint. So P3 is equal to what, P2 minus the delta, whatever the loss it's having, divided by P2. Okay, what basically I am doing, whatever the because you see P2, P3 will be what, it at the lower pressure. Okay, so what I done, if I just, because this is not a simple pressure value, like not a direct value, right? It's a change in pressure value. Okay, so what so you need to find out the what, the or in other way I can write down easy then. Or okay, P2 minus P3. Okay, P2 minus P3 is equal to what, delta PB by P2. Okay, you see it's written 4% of compressor delivery pressure. Okay, that means it's not a simple value like delta PB is not just difference of pressure, rather it's actually there with respect to compressor. They are telling this 4% there is loss. Okay, so we can just write down like this manner. The what is the difference in P2 minus P3 is not directly delta PB, rather it's P2 minus P3 is equal to delta PB with respect to what, with respect to P2. Okay, so from here we need to find out the P3 actually. Okay, so you have to use this expression. Okay, so P3 is equal to, okay, what is P2? P2 we already know. P1 we know. P2 we know here 3.144 bar. Okay, delta PV is 4%, which is 0.04. Okay, so 3.144 minus 0. Okay, just a second. No, just no. This is actually having. So okay, one thing we can do, instead of taking is a compressor delivery pressure, all this thing, we just assume it just as the combustion pressure loss. Okay, that's better. Okay, then it will be easy to understand, otherwise it will be a little confusing. Okay, what we will do, and just I will take like this, like P2 will be your 1 minus this. or P2 minus delta PB. Okay, that means okay, this P2 minus P3 will be your delta PB. Okay, so I can directly write down 3.144 into 0.04. Okay, like this we can just write down. Okay. So yes, so P2 minus delta PB. Okay, so just substitute 3.144 and this is obviously your 0.04. Okay, to solve you will get some 3.018 bar. Okay, so this is your answer. Okay. P3 you have. So yes, so now what we will do, we just now just a second, I think it will be 3.144 minus 3.1. Other way we will do 0.04 by 3.144. Okay, then minus 1 into 3.144. Okay, which is 3.104. Okay, so this is the answer. Okay, something. Three 3.104 bar. Okay, so now we have what? P3. Okay, so now we can find out the T for dash. Okay, or T for prime. So now how we'll relate this T for prime? Okay, for that one more term also given is the isentropic efficiency of the turbine. Okay, because 3 to 4 is your what is operating inside the turbine, but instead of having 100% efficiency, then it will be 3 to 4. But now it's the combustion efficiency, the turbine efficiency also not 100%. They are telling the turbine efficiency is only 90%. Okay, so we have to consider this 90% compression efficiency. Okay, sorry, the turbine efficiency. Okay, so how we are going to consider the formula for the turbine efficiency is equal to T3 minus T4 dash, the difference of actual temperature divided by the difference of ideal temperature. Okay, oh, I think it's the reverse. Sorry, it's reverse actually. Ideal by actual. Okay. Because if you see in the diagram, actually, which temperature will be high? You see your Okay, we see what is the temperature of T4, 992.3 Kelvin. Okay. So for T4 we have 992 point something Kelvin is there. Okay. So this T, but okay, so that means you see, that means if this formula satisfies, that means this T4 dash will be less than the T4. Okay, so that means in graph it is actually wrong. I just need to put other side. Okay, so this is how you can just understand the things. I'll just erase. It will be on this side. Okay. Okay. For this. So if you just directly found T4 dash is equal to T3 minus 1 by turbine efficiency into T3 minus T4. Okay, all right. Okay, so now if you substitute all the values, like 1200 minus 1 by 0.9 into 207.7. Okay. Because we know already T3 minus T4 is here, right? 207.7. Okay, and just substitute all these values. Okay, and if you find out the T4 dash is actually less than T4, which is 969.2. See, in actual practice it will always be higher. Okay, but sometimes it will be higher, sometimes it will be lower, because it depends on the whatever the efficiency is given. Okay, higher in the sense T4 always equal to T4 dash. Okay, and now it's actually less. Why? Because your combustion is not 100% efficient. Your turbine is not 100% efficient. That's the reason why your T4 is higher than your T4 dash. Okay, so now if you have T4 and T3, now we can easily find out what 4 to 3, because you see, and now for 3 to 4 process. Okay, if we directly we just consider the ideal case. Okay, 3 to 4 ideal case if you just consider, then you can easily calculate what P4. Okay, that is P4 by P3, the isentropy process if we consider, is equal to what? T4 dash by T3 to the power gamma by gamma minus 1. That means what you understand from here is your 3 to 4 process is not actually your in a straight line. Okay, because it's isentropic process, right? So 3 to 4 we are initially thinking, okay, 3 to 4 will be in the straight line, but now it's not in the straight line. Rather 3 to 4 dash is in the is just a straight line or a vertical line. Okay, and it's having and so it will follow the isentropic process relation. Okay, that means 3 to 4 days we can apply actually the isentropic process relation. Okay, which is a very important thing to follow, because from this only this temperature, so only from this temperature only we just see that, because it's less than your what 992.3 Kelvin. Okay, which is T4, Because of this only we get to know, okay, now this temperature is less, that means it is not going to be your actual process. Okay, it can be, this will be a isentropic process we are assuming. Okay, so yeah, so it's a, so like that you can actually think of what relation you need to apply. Okay, so that's P3 we already know. Where is P3? P3. P1 we have, sorry, P3 here. Ah, here. P3 I didn't calculate. I calculated, I think. Here is P3, right? 3.104. Okay, just substitute. Okay, so P4 by 3.104 is equal to 0. Sorry, 969.2 divided by T3 is what? 1200 Kelvin. Okay, to the power gamma by gamma minus 1. Now here you can think of one thing, because you see in the engine, it's now operating in a what? Which process? In the turbine it's operating. Okay, and for that your CPG is not your normal gas. Okay, so always remember this, when this air is considered, where there we only consider the gamma as the diatomic gases. Okay, now because of high temperature, this diatomic gas becomes what? Becomes a monoatomic gas. Okay, and it's having a gamma g of what? What is the monoatomic gas gamma value? 1.33. Okay, so gamma g we need to take as 1.33. So these are very small things, but if you remember, then it will be easy in your exam. 1.33 by 0.33, because they are not going to give all these values. What is gamma g? All these things. Okay, so you should remember. Okay, now it's in the okay, it's now in compressor. Compressor is obviously air compressor, and because of that we just consider gamma as 1.4. Okay, now it's operating in turbine. So the specific heat can at constant pressure is also going to change, and due to which there will be a change in the gamma value, which will be 1.33. Okay, unless and until it's mentioned that it's the value is this, you can actually consider this is as a ideal system. If it is mentioned this is a actual system, like this kind of question, okay, it is actually this kind of it's not at the normal atmospheric condition, or it's not at the normal altitude of 0 meter. Now it's at the 10,000 meter. Okay, so all this, because of these conditions only we can actually assume all these things. Okay, if it is at the normal atmospheric condition or normal height, then we can obviously going to take 1.4. Okay, so P4 we calculate as 1.284 bar. Okay, so now again in the question, we can see in the question, the next will come in most of the cycles in the Brayton cycle we stopped at actually 4. Okay, there is no 4 to 5 process. Okay, but in this actual system there will be, after turbine there will be a nozzle. Okay, on a convergent nozzle is kind of structure is there. Okay, to control the exhaust temperature. Okay, so so and in for a nozzle always we consider the pressure ratio. Okay, which is called as nozzle pressure ratio, which is equal to P4 by PA, which is what? 1.284 by PA is 0.265, which is 4.845. Okay, so why this nozzle pressure ratio is very important, that we will now see. Okay, because it's one similar term called your critical pressure ratio, which is extremely important term. Okay, and especially in this kind of actual cycles. Okay, what is the formula of, because in the question directly they will ask you, they will give you the this isentropic efficiency of the nozzle given, right? 0.95. okay, just they will give in the question one a turbojet engine is operating at a altitude of 10,000 meter. This kind of question can be asked in your exam, like not this much lengthy question. We can just take all parts, whatever the parts I done, it can be asked as a separate question. One very good question, if I am there, I will ask this kind of question, that one turbojet engine is operating at a altitude of 10,000 meter with a Mach number of 0.8. okay, this just find out the critical pressure ratio. okay, and the isentropic efficiency of the nozzle is 0.95. okay, this is the only question it will be asked. okay, it's 1 or 2 line question. okay, it will be asked. okay, and it's near impossible for you to solve if you don't know the formula of the what critical pressure ratio, because in the question nothing is given. You think, okay, nothing is given, how I will find? okay, so for that you should know the or remember these formulas, okay, of critical pressure ratio. okay, this is actually the critical pressure ratio, always calculated P4 by PC, always the what the nozzle inlet pressure to the critical pressure, okay, is equal to 1 by 1 minus 1 by eta of nozzle into gamma minus 1 by gamma plus 1 to the power gamma by gamma minus 1. okay, this is the whole power. okay, now here what is this gamma? okay, this gamma is not a simple gamma. Gamma is a gamma of G. okay. Don't confuse. Don't put gamma as 1.4, then gone. All this whole calculation over. okay, especially the gamma of the because after the turbine only the gas will come to nozzle, right? So the turbine, whatever the condition of gamma you are taking, same condition you have to use for the nozzle. okay, so here we see what is the gas. Now it will become monoatomic gas. okay, so monoatomic gas, the gamma G will be what? 1.33. okay, okay. And what is the eta J? Eta J already given 0.95. okay, so this is also gamma G. okay, now if you solve it, you get this P4 by PC ratio as 1.91. okay, so yes, this ratio is actually very important. okay, so there's two ratios we have. One is here what? Nozzle pressure ratio, which is 4.845. okay, and actually one is the what? The critical pressure ratio, which is 1.914. now if you can compare that P4 by PA, your nozzle pressure ratio is very greater than, nearly 4 times greater than your critical pressure ratio, then what will be the case? So this can be asked as a simple 1 mark MCQ question, theoretical question. okay, so the question is the condition if for a turbojet engine operating at a high altitude of 10,000 meter, the nozzle pressure is higher than the critical nozzle pressure ratio is higher than the critical pressure ratio. Then the nozzle is dash. Okay, it is going to work. It's going to choke. It's not going to. It will work. It's going to work as usual. Okay, something like that. And then none of the above. Like that, some of options will be given. Okay. So okay. Always remember, if there is no pressure ratio exist which can be higher than the critical value. Okay, if it is higher, that means the nozzle won't work. The nozzle having useless. It's having no use. Okay, it cannot be higher than the critical SI value. Okay, since here in this case our P4 by Py we get it as 4.845 and P4 by Pc is 1.914, which is a higher value. Okay, this is your nozzle pressure. And this is your critical pressure ratio. Since it's greater than, okay, so it's greater than, so what will happen? The nozzle will choke. This is very, very important statement. Okay, this you should remember. Okay, the nozzle will choke. If it is higher, then nozzle will choke. That means there is no use of the nozzle. Okay, in the engine. Okay, so let's find out the P5, T5, all these other parameters. So T5 is equal to Tc, which is the critical condition, is equal to 2 by gamma plus 1. Okay, this is the relation for your what? Nozzle. This formula we have to use. Okay, which is 2 into T4 we already know, 992.3 by gamma plus 1, 1.33 plus 1. Okay, you solve it, you will get T5 as 850.7 Kelvin. Okay, now P5 will be equal to critical. Now you can understand why I write down all these critical values. Okay, P5 equal to Pc. Now you understand. P5 equal to P ambit, you already know. Okay, just we are assuming it as Pa, but it's not equal to P5 is not equal to Pa, it's actually equal to Pc. Okay, so it's not Pa. Okay, it's not Pa. It's not Pa, it's equal to Pc. Okay, because of choking condition. Okay, so P5 equal to Pc is equal to P4 into 1 by P4 by Pc. I can write down, right? So why I am writing down like this, because P4 by Pc you already know, right? So P4 is already, you know, 1.284. Here you know P4. Okay, 1.284. Okay, and P4 by Pc also you know 1.914. Okay, just substitute, you will get P5 as 0.671 bar. You have T5, you have P5. Okay, that means everything we have now. Okay, just we have to need just one thing we need, that is the density. Okay, that is rho 5, because now it's actually at the nozzle which is near to the ambient condition. We can now apply ideal gas equation. Okay, rho 5 is equal to rho equal to P by RT. Okay, so which is PC by RTC. Okay, is equal to 0. PC we know 0.671 bar, and 1 bar is equal to what? 100 kilopascal. Okay, okay, so 671 into 100, I'm converting into kilopascal, kilo unit. Okay, R also 0.287 kilojoule per kg Kelvin. Temperature is your 850.7 Kelvin. Okay, which is your what? T5, and you know very well T5 equal to what? Is equal to TC is equal to. Okay, so now this rho 5, if you solve, we will get 0.275 kg per meter. So why I am finding this rho 5, that also we now see. Let's now find out the sonic velocity C5 is equal to gamma RTC square root. Okay, gamma of Z you know 1.33, R you know 0.287 for the air. Okay, and PC you know 850.7. Okay, but this is it should be noted that for this expression you cannot put actually what kilo unit, you have to convert it into what, in the SI units. Okay, in joule. Okay, joule per kg Kelvin. So 0.287 into 10 to the power 3 joule per kg Kelvin. So now C5 will be equal to, if you solve it, you will get very high velocity. You can see 570.5, nearly Mach 2. Okay, we are operating at a Mach of 0.8, but now you can see it's nearly achieving more than 1, greater than 1. That means that the speed is nearly supersonic. Okay, supersonic velocity we are observing. Okay, yeah, so C5 is your 570.5 meter per second. Okay, and let's also one more parameter let's find out, which is your A5 by m dot. Okay, so all these things you will get to know why I am finding. Okay, your area, cross sectional area A5 divided by mass flow rate m dot. Okay, is equal to what? 1 by rho 5 into C5. Okay, this is the formula. Okay, okay, so 1 by, now you understand why I find out rho, because to find out this A5 by m dot, okay, I just find out the rho 5, and C5 also for that this same formula I just find out. Okay, so just substitute whatever you just find out, rho 5 and C5. Okay, if you just substitute all these things, you get the value as 0.006374 meter square second per kg. Okay, so just now it's about to get over. Okay, now we can find out the specific thrust. Okay, the specific thrust Fs. Okay, so Fs is equal to C5 minus Ca. C5 is the critical condition, C is the ambient condition, plus F5 by m dot into PC as the critical condition, PA as your ambient. This is the very important formula for the specific thrust of any kind of turbojet engine. This formula can be applied. Okay, so just need to substitute all these values. 570.5 minus 239.6 plus 0.006374 by m dot. Okay, okay, uh, huh, huh, into PC 0 what is PC 0.671 minus 0.265, but this is in what bar 2 kilo Pascal. How you will convert? Put 10 to the power 5. 1 bar is equal to 10 to the power 5 Pascal. It's very very important to know the units. You see, every times units are very very important. Okay, yeah. So next we solve it and find out the thrust. Our one answer we have now, at least, that is 589.7 Newton second per kg. Okay, so this is your answer. Okay, one more answer we need. Okay, for that we need the theoretical. Okay, so one more things we need from the question. Okay, in the question, it's not given. Okay, okay, whatever. For this, you see, for this 10,000 meter on all these things, they should give actually in the question what is the fuel air ratio. Okay, otherwise it's very difficult for you to calculate. This value should be given. Okay, fuel air ratio theoretical will be 0.0194. This value they should give. Okay, because in that condition 10,000 meter, what is the fuel air ratio? Okay, how much fuel is there, how much air is we are operating, that we don't know, right? So those things we need. Okay, till that in that table of 10,000 meter, the fuel air ratio they will mention. Okay, in that in this condition, this is the value. Okay, so why I need this value? Because the because in the question one more thing condition given is the what your your question in the question is given combustion efficiency of 0.98. That is the that's why we need it. Okay, so this combustion efficiency we have 0.98. Okay, so what is the formula of combustion efficiency? The combustion efficiency is equal to the fuel air ratio theoretical divided by the fuel air ratio actual. Okay, theoretical value they should give, otherwise it will be difficult. Okay, so now what we need to find out the actual fuel air ratio. Okay, the actual fuel air ratio we need to find out. Okay, which is equal to 0.0194 by 0.98. If you solve it, you will get 0.0198. Okay, this is the value you will get. So okay, now what is the formula of specific fuel consumption? Okay, thus specific fuel consumption, SFC. This is a very important term. Okay, SFC is equal to the actual fuel air ratio divided by what? The specific thrust. Okay, this is why we need we do all this hard work to find out this Fs. Okay, because unless and until you know Fs, you cannot find out the specific fuel consumption. Okay, so this value will be 0.0198. Okay, mostly this specific fuel consumption are denoted in hour units. Okay, per hour how much fuel is consumed. Okay, so for that I just multiplied by 3600 sec 1 hour 3600 seconds, right? 1 hour 3600 second divided by your thrust power is 589.7. Okay, you just calculate, it will be 0.121 kg per hour Newton. This unit is also very important. Okay, this is your answer. Okay. Very important. This formula is also very important. So thank you very much for attending the section. If you have any doubt, you can ask in my comment section of my channel. My name Sumit Sagar Hota. Okay, thank you very much for patiently listening whatever I am teaching. Okay, we'll meet next week 6 to 8 Saturday. Okay, thank you and good night.